Let's recall from the last class. That given a symmetric form on some vector space, a real vector space, say, we call this form positive. Well, let's note it down here. One positive definite. Let's, for shorthand notation, let's write it just plus v definite or semi definite if VV is greater than 0, or, okay, here or might look like a division, so let's write it down just or VV greater than equal to 0. Okay, that was positive definite or positive semi definite. We can. Sure, yes, of course, yes. So for all v in v minus 0, because we saw that if it is in particular 0, this is just, I mean, it should be equal to 0, right? Second is negative definite or negative semi definite if this VV is less than 0 or VV is less than equal to 0, again for all v in v minus this. Okay, and then third, indefinite if this is neither positive or negative definite or semi definite. Okay, and then we saw also an example. Well, we described just that curious example. Covariance defines a positive semi definite bilinear form on the space of, on the vector space of real linear combination, okay, real vector space, like we can write on the real vector space defined by the span of a finite set of random variables. Because you do not know what random vectors are, just take a finite set of random variables, call that your random vector. Okay, so the span of a finite set of random variables, in fact that is a random vector. Okay, well, all defined on the same sample space. Okay, otherwise how do you define, I mean, how can we say about covariance between two such things if they are not defined on the same sample space? Okay, and in particular the Gram matrix of this form will be called the covariance matrix. Okay, we call its Gram matrix covariance matrix. Okay. So that's an example of positive definite form and a positive definite matrix. I mean, soon we are going to define, no, we are not soon going to define, we are defining now. That is, we are defining immediately what we mean by positive definite matrix or a positive semi-definite matrix. Okay. This part of the board I can clear up, but nevertheless, I don't think all of you have finished writing. So let's use this part. Okay. So we call definition. We call a matrix positive or negative, definite or semi-definite if it is the Gram matrix of a positive or negative, definite or semi-definite form, bilinear form respectively. Okay. I think you have seen already what are random variables there, right? So it's a map from the sample space to the reals such that the pre-image of any interval is measurable. The probability of that is defined. Okay. Yeah. The covariance of two random variables? Sure.
So how does covariance define just a positive semi-definite?
What? I haven't understood again.
The covariance defines a positive semi-definite.
Yes. What is the definition of a positive definite or positive semi-definite form?
All the linear products are greater than 0.
All linear products?
All the bilinear products, bilinear forms are
No. What is this? What are the arguments? They are the same arguments. So it's not some V and W. It is V and V. So what is the covariance of a random variable with itself? Variance. Is it ever negative? It's not. Right. Okay. So now, well, is it fine? I mean, what we define. The definition of a positive or negative definite or semi-definite matrix, is it understandable? That is, if you have a form, you know when it is positive or negative definite, right? And you know what is the gram matrix of a form, right? It is just the outputs of the form if you input the basis vectors of some basis, right? So Vi Vj is the ijth entry. Okay, and then if a given matrix represents the form, that is, if it is the Gram matrix of the form with respect to some basis, we call the matrix positive definite or negative definite or positive semi-definite or negative semi-definite if the form is so. In particular, what does it mean? I hope now the first part is clearable. Thank you. Suppose our vector space is V, and let G be a basis. Not G. Sorry, B be a basis of a vector space V. Okay, and let G be the matrix of a form defined on V. Okay. Suppose this is a real vector space, okay, and suppose this is a form from V cross V to R, okay, and G is the matrix of the form this. Okay. Then suppose V is given by V is some element in V which is given by a linear combination X, a column vector, which is denoting the coefficients of the basis vectors. Okay. So V is Bx and say W is equal to By. Then do you recall what is the relation between VW? I mean, how can we express this product in terms of the gram matrix X and Y? Perfect. X transpose Gy. Okay. So in particular, for a matrix to be positive definite, I mean from here, then this means that a matrix A, say, is positive definite, for example, if and only if, fill up the gap, Manas. So X transpose Gy was this form, right? Now, I hope you recall what is a positive definite form, right? If you put V there, it is always positive. Okay. So wait, let Manas tell, because he had the doubt earlier. So I hope, I mean, if he has understood this clearly, then he would be able to tell, please. So in both arguments, you should put the same vector, okay, and the output will be positive. Then tell me what you get here, putting V in both arguments. X transpose Gx. So here we took the matrix to be A. So X transpose Ax, right? X transpose Ax would be positive, right? So that's the definition of a positive definite matrix. Okay, and similarly you can get the other ones. Okay, and this is true for, because X is a coordinate vector, right? So X could be any vector. Okay, so this is X at 0, of course. So this is true for all X not equal to 0. Okay, all right. Now, in the last class, we have seen that if our dot product, the usual dot product on Rn is represented by some other matrix, it should be of the form what? P transpose P. Wonderful. Yes. Okay. So let's write it down here. Okay. So here's a proposition. You can write it down as an exercise if you wish, but it's called a proposition because it is useful also. Okay. Not just an exercise, it is useful also in the other exercises. I'm on this, but what it means, I mean, what it states is that the following are equivalent. Given a matrix A in M n R. One. A is the gram matrix of the dot product with respect to some basis of Rn. Okay. The second is that there exists P in GLNR such that A is equal to P transpose P. Okay. So there exists some invertible matrix such that A is equal to P transpose P. And the third which is the exercise, is that A is symmetric and positive definite. Now this one, the last one, we saw the equivalence of the first one in the previous class. Okay. The last one is a really non-trivial exercise, okay, for which we need to define at first some concepts called orthogonalization, some concept called orthogonalization, and even before that we must define what is an orthogonal basis and what is an orthonormal basis. Okay. So today we will prove this, but this will require a little work. Okay. So in particular, you can mark that as a really difficult exercise, okay? Because if we try that directly without the tool that we are going to introduce, it might be really wild. Okay. So at first, define what is an orthogonal basis. And even before defining orthogonal basis, we must define what are orthogonal vectors. Excuse me. So two vectors, well, given a symmetric form, symmetric bilinear form, from V cross V to R. Well, note that this definition of orthogonal vectors will later also generalize it to other kinds of forms called Hermitian forms over vector spaces on complex numbers, okay, on the field of complex numbers. So here we just take a symmetric form and even a symmetric form this for two vectors V and W in V. We write V is perpendicular to W, and say that V is V is orthogonal to W. Okay. That is V is orthogonal to W if VW is equal to 0. It's a symmetric form. That means also WV is equal to 0. Okay, so yeah. No, bilinear form need not be always symmetric, but we are defining orthogonal forms for symmetric things. Well, actually, we will specialize on symmetric bilinear forms. Okay, and working with symmetric forms makes our life is going to make our life rather easy. Okay, and the main theorems on bilinear forms, which we are going to prove, are all on symmetric forms. But bilinear forms are of course more general. So if you want to study other kinds of forms, that is which are not symmetric, you are free to do that. Okay, but the theory that we are building up will be mainly about symmetric forms. So we are just specializing there. Okay. So this is the definition of vectors V and W which are orthogonal to each other. Okay. Now we just defined orthogonal vectors, and then we can also define in the same go we can also define what are or spaces orthogonal to other vectors, I mean subspaces. Okay. So in the same go, let's define also orthogonal spaces. Okay. To a given orthogonal space to a given subspace. W of V, say. Okay. How do you define this? Okay. We denote it by W perp, okay, and we define it to be all the vectors V in V such that VW is equal to 0 for all W in W. Okay. So, a set of all vectors which are perpendicular to all the vectors in W. Okay. We said that we are going to prove this, and now if we wipe this out, that's really bad. It doesn't matter. Okay, as long as their inner product is 0, we are going to call them perpendicular on each other. Okay, and we will see situations where V is perpendicular to on itself. Okay, so V is like self orthogonal. Okay, that will be also a situation that we will consider. Okay, so it's not that you can always geometrically visualize what it is, but we'll just go with this definition. Okay. In particular, this matches with the definition of perpendicular vectors in R2 or R3 with the dot product that you have seen. Okay. Yeah, self perpendicular just means that if you put V there, it is equal to 0. So in particular, if some vector, if your vector space contains one vector which is self orthogonal, that means that your form is not positive definite, okay, or not negative definite, because we are having a self orthogonal non-zero vector. If you are having that will mean that your vector space is having a non-zero vector for which this bilinear form is not giving a positive or negative output. Okay. So in particular, that means that the form is not positive definite or not positive negative definite, could be semi-definite nevertheless. Okay. Okay. Once we have defined orthogonal space, both the notion of orthogonal vectors and orthogonal space could be generalized to Hermitian forms, which we will see later. Okay. And then we define null space. Okay. Null space of a form. Okay. And we denote it by n. And suppose the form, wait a minute, suppose the form is from V cross V to R, then we call the null space of the form as, we define it to be the vectors which are perpendicular on all the vectors in V. Okay. All right. That is V in V such that VW is equal to 0 for all W in V. Okay. Why we are calling it the null space will soon be clear. Okay. This has to do something with the null space of the Gram matrix. Okay. Which one? Well, it's orthogonal space. Null space is in particular a space orthogonal to the entire vector space on which the form is defined. Okay. So this is just a specialization of the orthogonal space to a subspace. Okay. Here the subspace is the entire space V itself. Okay.
So when you say for all W belongs to V, does that include V itself?
Yes, of course. Yes. So in particular, null vectors are these are the elements of n, okay, or V bar, whichever you prefer to write. Okay. So the elements of all the vectors in the null space will be called null vectors. So existence of one null vector, one non-trivial null vector, would mean that that this is a non-trivial space, and that would mean the form, that's the same as saying that the form is non-degenerate. So we define a non-degenerate form. Where should we write now? Can I clear up that part? Because I don't want to wipe the proposition. We will do the last part of the proposition soon. Okay. So now we call a form non-degenerate form is a form with null space equal to 0. Okay. So the trivial null space. If your form has, no non-trivial vector in its null space, we call the form non-degenerate. Okay. Otherwise, we call it a degenerate form. Okay. And most interesting examples of the forms which we will note will be non-degenerate. Nevertheless, we can say a little more about degenerate forms, but maybe later, because we have to come back here and prove this first. Okay. Okay, just one thing, because we defined already the null space there. So this you may take as an exercise that we prove in the next class. Okay. So a form is non-degenerate if and only if it's the determinants of, it's gram matrix, sorry. Gram matrix with respect to a basis or any basis is non-singular. Sandeep? So please note down the exercise. Okay. All right. It seems that you are sleeping. So yeah, this actually is a rather non-trivial exercise, but nevertheless, you can see that the gram matrix is non-singular and the form is non-degenerate. This has a connection with the fact that we are calling this a null space. So you can understand which vectors are going to be the null vectors, which are in the null space of the gram matrix. Whose coordinates are in the null space of the gram matrix. Okay. Yeah. Yeah, the non-degenerate forms are those for which the null space of the entire vector space is trivial. Okay. This one is trivial. There are no non-zero vectors in it. Okay. 0 is orthogonal to everything, because 0, take the bilinear form, I mean put 0 in one of the arguments of the bilinear form, you will definitely get 0 on the other side as an output. But except 0, there are no other vector which is giving you 0 output. Okay. In that case, we say the form is non-degenerate. Okay. And non-degeneracy of a form is equivalent to saying that the Gram matrix is non-singular. Okay. Otherwise, you will have something in the null space of the matrix, because its determinant is non-zero, so Ax equal to 0 will have a non-trivial solution, and you can show that that x will form the coordinate of a vector which is a null vector. So the null space is non-trivial. Okay. All right. Now about the proof of this, can I wipe out the definition of null space? Thank you. Okay, so now we are going to learn something which is called Gram-Schmidt we haven't defined what is an orthonormal basis, did we? Neither orthogonal basis, did we? Okay, so now an orthogonal basis first, because it's called Gram-Schmidt orthonormalization procedure. Okay. And I must explain first what is orthonormalization before giving you the procedure. Okay. So we are going to explain this soon. Okay. And this procedure is going to be rather important in the rest of the course, because we will use this procedure again and again. Okay. In a moment, we will be back to that after defining what is an orthogonal basis and what is an orthonormal basis. Okay. So again, let this from P cross V to R be a symmetric and now positive definite as well. Okay. Positive definite bilinear form. Okay. Then we call a basis B an orthogonal basis if Vi Vj is equal to 0 for all I not equal to j, where these Vi's are just the basis elements. Okay. Okay. So starting with this basis, and then this just means that if you are putting Vi and Vj as the arguments of your bilinear form, which is symmetric and positive definite, okay, so we are going to define those as inner products, okay, symmetric, and we will come back to this soon, because once we define Hermitian form, we will do this in one go. Okay. But on a real vector space, a symmetric positive definite bilinear form will be called an inner product. Okay. Yes. What? I haven't understood. Again. Right. It depends on the basis. Sorry, it depends on the form. That is, what do you mean by inner product or the output of? So what I want to say is that the if you have to define kinds of bilinear forms, the output of V and W in two different forms will be different. Okay. In one form they might be orthogonal to each other, in another they might not be. Okay. Exactly. We will say that this is an orthogonal basis with respect to this form. Okay. So this is an orthogonal basis, of course, with respect to this form, the given form. Okay. That's implied because here we are just taking this as our form, but of course this one is with respect to this given form. Okay. All right. So that's an orthogonal basis. And how would the gram matrix look, Orkodeep, in terms of an orthogonal basis? Suppose you are given a basis B, which is orthogonal with respect to the given form, then the corresponding gram matrix looks like what? It's, of course, it's symmetric positive determinant, but can't you say something more? It's diagonal, because you see all the Vi Vj's are 0, except when we do not know when I equal to I mean when I and j are equal, what happens? I mean, on the leave the diagonal entries, but everything else is 0. Okay. Again, now the orthonormal which or not always. Now, well, if you are taking this to be positive definite, yes, actually, but well, for defining orthogonal basis, this was still not required. Okay, we will require this now when we define orthonormal basis, because here we have never used the positive definiteness. Okay, so for orthonormal basis, well, we call the basis, or we call a basis B, an orthonormal basis of V if the first condition is satisfied, it's orthogonal. Moreover, so if B is orthogonal, of course, as Orkodeep pointed out, with respect to the given form, and moreover, now we have to say something with these VI's, VI here, okay, and VI is equal to 1 for all I. Okay, so all the diagonal entries are 1. That means if you have an orthonormal basis, then the gram matrix of the form with respect to the orthonormal basis is identity. Okay. Now we come to this Gram-Schmidt orthonormalization procedure. What it will do? It will start here. We'll have a symmetric and positive definite form. Okay, that is A is the corresponding matrix. Okay. So we'll start with a symmetric and positive definite form, and we'll show that given such a form, there always exists such a basis, an orthonormal basis. We'll start with any arbitrary basis of the vector space, and we'll end up with an orthonormal basis. Okay. So what does this procedure do? It produces, it's an algorithm that you can actually type in a computer. I mean, you can write a program which takes up any basis of your form and outputs an orthonormal basis. Okay. So this is an algorithm which outputs an orthonormal basis given an arbitrary basis of vector space V, a real vector space. Actually, we'll later say that this orthogonalization procedure is also extendable to Hermitian forms, okay, positive definite Hermitian forms. Trishit, yeah.
Where did we use the idea that the Albion form is positive definite?
Yes, that's actually a very good question. So here, till now we have not used anything. We just, I mean, symmetry just means that Vi Vj is equal to Vj Vi. Okay, so it's a symmetric matrix. That's all. Okay, with all zeros everywhere. On the diagonal, we do not know anything. Okay, but on the diagonal, what sits there? Vi Vi, right? And then what we are doing, we are scaling those Vi's with some scalars. Actually, we are dividing by their lengths. Okay, so yeah, wait a minute. Let's give the concept one by one. So, given such a form, the length of a vector, which we denote by this, would be given by this, and we can write this VV square root, because this is always positive for a V non-zero, okay, and when V is 0, this is just 0. Okay. So that means this you can define as the length of the vector, and now you are scaling the vector with the length. So you are dividing it with the length. Okay, you are making it length 1. And what will that mean? Let's write it down somewhere here. Orthogonal basis. I hope we can write this out. Okay. So this, let's define this as the length of a vector with respect to a positive definite length of a vector with respect to a symmetric and positive definite form. Okay. And this symmetric and positive definite form, this we are going to call an inner product. Later, we'll, instead of symmetry, we'll have Hermitian symmetry. That is something else. And those also we'll call as the inner products over complex vector spaces. Okay. Soon, perhaps in the next class, we'll see what are Hermitian forms. Okay. All right. Now, suppose you have these Vi, Vi's. You don't know what these are yet. Okay. But you know that if V is non-zero, then this is, the length is non-zero, right? Because it's a positive definite form. Okay. So instead of taking Vi, you can scale it down. So you can define some Vi dash as Vi divided by the length of Vi. Okay. Then consider this. Note that this is still in the span of Vi. Okay. So we are choosing some other vector from the line. Which one? The one with the unit length. Shivam, are you all right? Okay. So then you have this Vi dash, this is equal to Vi by norm Vi and Vi by norm Vi. Recall it's a bilinear form. Norm or length. Okay. So now, since it's a bilinear form, what happens? The scalar multiple, this is a scalar, right? So this goes out. It's a scalar. This goes out as well. Okay. So outside what you have? The square of this. What is the square of this? No, it's the square of this is just Vi comma Vi. Okay. So that means this is equal to just, I mean, outside you are having Vi, and here you are having Vi. So now you can cancel and you can get the 1. Okay. So this is giving you 1. Okay. That means this one, what you get by dividing Vi with its length is a unit vector with respect to the given norm. Okay. So that's how, given an orthogonal basis, if your form you know that it's a positive definite form, you can always normalize it, so that all the vectors all the vectors in the basis are having length 1. Okay. And thus we get an orthonormal basis from an orthogonal basis. Okay, and what does this algorithm do? It outputs an orthonormal basis given an arbitrary basis. So you are not even starting now with an orthogonal basis. You are starting with an arbitrary basis of the vector space. You are having this. So I don't think we have enough time to describe this algorithm now because it's already 9. But once we have this algorithm, note that what we will be given. Let's write it down at first. What we have here. Okay, orthogonal basis given an arbitrary basis of a vector space V with a symmetric and positive definite form on it, form defined on V. Okay. So you are having a symmetric and positive definite form defined on this vector space V. Then in your program you are inputting some arbitrary basis of the vector space, and the program is outputting some orthonormal basis. Okay, and so A is symmetric and positive definite. That means what? With respect to the standard basis, for example, this defines a symmetric and positive definite form, right? Not only with respect to the positive, the standard basis, with respect to any basis. Okay, this defines. If you take this to be the gram matrix with respect to any basis, this is just we saw that the form is symmetric if and only the matrix is symmetric, and similarly it will follow that if the form is positive definite, that is that was a definition actually for a matrix to be a positive definite matrix, right? So what we will do now, we will take that form, okay, and we know that then there exists, once we have the Gram-Schmidt procedure, we know that there exists an orthonormal basis. Okay. Now, what is the matrix of the orthonormal basis? What is the gram matrix of the orthonormal basis? Identity. Okay. So if you start with an arbitrary basis and this as your gram matrix, so if A is the matrix of the form or the gram matrix with respect to a basis B, and say A dash is a matrix of the form with respect to an orthonormal basis, then where we should write maybe that part of the board. So we know how the matrix of the form changes from one basis to another, right? So B is an arbitrary basis, not arbitrary, arbitrary basis with respect to which A represents the gram matrix. Basis with A as the gram matrix, and B dash is your orthonormal basis. And suppose A dash is the corresponding gram matrix with respect to B dash. Okay. So how do we go from, what is the relation between A dash and A? Recall, P transpose AP was A dash, right? Okay, so A dash is a gram matrix with respect to B dash, and suppose we have B dash equal to BP, okay, and that will mean, since it's an orthogonal basis, A dash is just equal to identity. We are going to use that fact later, but at first we have A dash is equal to P transpose AP, right? And then that would mean, since this is identity, identity is equal to P transpose AP, okay? And remember, P is invertible, okay? So P transpose AP is identity. That is coming from the Gram-Schmidt orthogonalization procedure, because there always exists an orthonormal basis. Okay, and then just multiply with the inverse of P inverse and P inverse transpose on the right hand side. So you get that A is equal to Q transpose Q, where Q is equal to P inverse. Okay. So A is indeed of this form. Okay. All right. And note that this is not a, I mean, what I want to say is that this is not a one-way proof. Actually, this is a both-way proof. Okay? Because if you have this, then that would mean that there exists some orthonormal basis. Okay? So we are done. Okay. And once there exists an orthonormal basis, it means that that represents a dot product with respect to that. Okay. So thus we finish the proof of this proposition modulo Gram-Schmidt process, which we have not seen, which we are going to see in the next class.